Hello and welcome everybody. Myself Sudarshan, rule number 20EE10075. In this video, I am going to demonstrate my experiment number 5 of Digital Electronic Circuits Lab. Here the aim is to get familiarity with hex keypad and ALU and its use. For this experiment, we are using the ASCII keyboard. So let's move to part A of this experiment. Part A says that we have to verify the truth table of ASCII keyboard. ASCII stands for American Standard Code for Information Interchange. So that means, as the name suggests, this is the code which will convert any data or any character or number into some sort of conditions. Like if I am inputting here 2, then it will display 2. Similarly, if I am inputting here G, any ASCII character, then it will display this, which is displayed in the logic displays. Similarly, for 9, 4, this is displaying. So, for one observation here is, when I am inputting any characters or numbers here from the keyboard, the strobe of this keyboard is blinking. So, this part can be better understood from the upcoming parts. So, let's move to part B of this experiment number 5. Here the aim is to store the values through IC 74374. So IC 74374 is an 8-bit register here. This is the clock pulse, and this is the enable, which is active low. These are the inputs and these are the outputs. So here the strobe is connected to the clock. When the strobe will blink, then it will activate the pulse, the clock here. So here we have to store the values. That means whatever the input here, it will be stored. So let's verify this first. So suppose I am inputting here first 5. Here it is 5. Then I am putting here 2. So 5 is going there and 2 is stored here. So this is also called a sequential circuit because the output is also depending on the previous values. Similarly, suppose I am inputting here 7. So here 7 is displaying. Similarly, if I am putting 1, then here 1 and the 7 is here. So in this way we can store the values. Now let's move to the next part. Here the aim is to design a subtractor or adder circuit taking inputs from the ASCII keyboard with the control input to be set manually. So how to design a subtractor or adder circuit? The basic idea is being displayed in the previous experiments. So here what I have done, I have used the XOR gates and this Cin, which is either active low or active high according to the need of this experiment. For addition, this should be active 0, active low, and for subtraction it should be active high. Suppose I have to do addition. For that, first let's run the circuit. So first I am inputting here 2, then I am inputting here 5. So here this is 5, so I have to put it active low. So this is 7. So 2 plus 5 is 7. Similarly, 3 plus 6 is 9. This is the carry generated, the logic display, and this is the MSB and this is the LSB. To do subtraction, I have to put this to high, and let's do 8, then 5. So 8 minus 5 is 3. So here 3 is being displayed, and this is the carry generated, which can be neglected. Similarly, 2 minus 1, which is 1. So in this way, I have designed the subtractor and adder circuit in the same circuit design. Now let's move to the next part of this experiment. Here the aim is to design a digital calculator. So in the previous part, the Cin has to be put manually, but here what I have done, that set of condition is also defined by the user. That means the user will define whether he wants the addition or subtraction. For addition, I have defined the operator as plus, and for subtraction, I have defined the operator as minus. Here I have written the lower 4 bits of ASCII plus is 1011 and the lower 4 bits of ASCII minus is 1101, which we have defined or verified in the part A of this experiment. If I am putting here any character or number, it is being displayed, and this display is the lower 4 bits of that ASCII character. So for that, I have to consider here that when this is 1011, for that condition the Cin should be 0. Similarly for 1101, this should be active. So considering this in mind, I have just used one inverter here. I've connected this to Cin. I can also connect these terminals to Cin. Obviously it will work fine. So I have designed in this way, and this is the IC74374. This is also IC74374, and this is the adder circuit, the first adder circuit, that is IC7483. These are the XOR gates. This is the LSB bus and this is the MSB bus. So let's verify this first. Let's run the circuit. Here suppose I am inputting here 2, then plus 5, that is 7, which is being displayed here. Similarly 8 plus 1, that is 9. Now to do subtraction, suppose I am inputting 9, then minus, then 4, this is 5. Similarly 7 minus 3, which is 4. So this is also working fine. Now let's do next part of this experiment. With the previous part, I am finishing with the experiments. I am left with the additional parts. So let's do those also. Here the aim is to verify the truth table of IC74181. IC74181 is an ALU, which is also called the arithmetic logic unit. By using this IC, we can do multiple operations by different conditions of those functional select inputs S3, S2, S1 and S0, and this is Cn and M. So by varying this, we can do different operations. These are the inputs A3, A2, A1, A0, and B3, B2, B1, B0. These are the outputs A3, F2, F1, F0. This is the comparator A equal to B. This is the carry generator, and this is the carry propagator. So I have it has a truth table also. So for the ease of verifying the truth table, I have defined something here which we can verify here. Suppose for addition, the aim is 0, Cin is high, and this is the condition for the S3, S2, S1 and S0. So this is 1, 0, 0, 1, this is 0 and this is 1. So this is the condition for XNOR. So let's verify first the addition. 1, 0, 0, 1, 1, 0, 0, 1, then Cn is high, and M is 0. Let's verify this first. So here you can see that the input here is 7, 0, 1, 1, 1, and this is 0. So just the addition is 0, 1, 1, 1, which is 7. We can also check for the XOR part. So let's it be 0, 0, 1, 1, and this 0, 0, 0, 0. For XOR, we have to change the condition, that is M is high, Cin is 0, Cin is high, sorry, and 0, 1, 1, 0. This is 0, 1, 1, 0. So this is the XOR because this is 0, 1, 1, and this is 0, 0, 0, 0. For the same inputs, the XOR output is 0. For different inputs, the XOR output is high. So it is verified, and for the other parts also we can verify easily. So here one observation is, for any arithmetic operation, the aim is 0 and aim is 1 for XOR and XNOR. So with this idea, let's move to the next part. The next part says that we have to design a subtractor adder circuit taking the inputs from ASCII keyboard and IC74181. So I have designed the subtractor adder circuit in the part D of this experiment. So but here I have to use the IC74181, that is the ALU here. So I have defined the operator as plus for addition and minus for subtraction, and these are the conditions for addition and subtraction here. So these are the circuit designs. So I must care that when I am pressing plus, this sort of conditions should be verified at the ALU side, such that the circuit will do addition. And when I'm pressing minus, this will do subtraction. So by those logics, I have just connected those lines into those points. So it can be explained very easily, because I can see that S3 is S0 and Cn is equal both the cases, and S2 and S1 are 0. So for addition, what I have done, I have connected this because for addition the lower 4 bit ASCII is 1011, so 0 is connected to S2 S1 and 1 is connected to S3, which is obviously connected to the S0 and CL. For both the cases aim is active low, so therefore I am putting it to the ground. Now let's verify the circuit first. Suppose I'm 5 plus 2, that is 7. Similarly doing 7 plus 3, that is 10. Now I'm doing 8 plus 1, that is 9. Now I'm doing subtraction. Suppose I'm 9 minus 2, that is 7. 7 minus 8, you can see here this is something coming else, because we have to take the 2s complement of this to get the final output, because we are doing the 7 minus 8, not 8 minus 7. If we are doing 8 minus 7, then it's coming 1. So this circuit is also working very fine. Now let's move to the last part, obviously the additional part, and this is nothing but the extension of the previous part. And here the aim is to design a circuit using IC74181 and ASCII keyboard, which will do 4 operations according to the defined operator pressed from the ASCII keyboard. So let the 4 operations be addition, subtraction, XOR and XOR. For addition, I have defined the operator as plus. For subtraction, I have defined minus. Similarly, X and N for the XOR and XOR respectively. So I have verified this in the experiment E, in the part E of this experiment. So for these conditions, it will do addition, this ALU. For these conditions, it will do subtraction. In the last part, where I have to design only the adder and subtractor circuit, there were only 2 conditions. But here there are 4 set of conditions. Plus, minus, X and N. All of these have their lower 4 bit ASCII values. With that, we have to match it with the functional select inputs Cn and Am also. So keeping those in mind, I designed this combinational logic such that if I am pressing plus, then this set of condition will be verified and the circuit will do addition. If I am pressing X, then it will do the XOR operation. So let's verify this first. Suppose I am pressing here 2 plus 3, which is 5 being displayed here, MSB to LSB. Those terminals can be neglected for the time being. Now let's I'm putting 5 plus 3, that is 8 being displayed here. Now let's do subtraction. Suppose 9 minus 8, that is 1. 5 minus 3, that is 2. So now let's do XOR operation. So I am inputting here suppose 7. For XOR, I have to press X in the keyboard, that is X. Then I'll do it XOR with 0. So 0 1 1 1, XOR with 0 0 0 0, it will give 0 1 1 1. So for the same set of conditions, let's do the XOR so that we can easily verify, because the XOR will be 1 0 0 0 0. So for that, let's put first 7. For XOR, we can see I have defined the operator as N, so I will put N here and then 0. So it's giving 1 0 0 0. So I have verified these circuits, and this is the last part of this experiment. So with this, I'm finishing up with all my experiments, but I must say here, we have done from experiment 1 to experiment 5. So we are leveled up from level 1 to level 5, and now we are rewarded with this magical key, that is IC74181, which is also called the ALU, because this is the entrance, this is the gate for the vast world of digital electronic circuits. By this, we are just introduced to the vast area of digital electronic circuits, and I hope with this key having with us, we will enter that and we will discover many things, because this is just the introduction. There are many things to discover and explore. So, but here I'm very sorry to say that this is the last part of my last experiment. So here I'm remaining here, but I must say a thank you to all to be very patiently listening to me. I am also thankful to you, and with this I'm finishing up with my experiment. Again, thank you so much.